In this mini lecture, I'm going to talk about state of stress and strain on a 2D plane. In the previous experiment, we have learned that the stress and the strain are directional. That means the value are dependent on which direction you are taking the measurement. The dependency of orientation or direction is problematic in practice because in most cases, we want to know which direction has the maximum value. And it's very cumbersome to attach a number of strain gauge to measure all the possible we can. Okay, and sometimes we care about a certain orientation. For example, this pressure tank, which has a welding line in a diagonal direction, and the welding line usually has a lower strains, and that's the weakest point of the pressure tank. And we want to know the stress and the normal stress or tensile stress or shear stress applying on the welding line. Okay, the question is how we can calculate the value of stress or strain at any orientation we want. So to do that, we need first to define the state of stress or state of strain. They both share a lot of similarity. Here, for example, to determine the state of stress, we need to have a defined orientation that is x. So on this x, we draw a rectangular member, and we need to know three variable. The first one is the normal stress pointing to the x direction, that is sigma x. The second one is the normal stress at the orthogonal direction to x, that is sigma y. And the third one is the shear stress, tau xy. Similarly, we need three value, that is epsilon x, epsilon y, and gamma xy to determine the state of stress. And in a 2D plane and isotropic material, tau xy equal to tau yx, and gamma xy equal to gamma yx. Once we determine the state of stress for a given x direction, the different direction of x prime can be considered as a change in the coordinate system. So in mathematics, there is an equation to calculate the changing of coordinate system simply by assuming rotating the xy coordinate by an angle of theta. Okay, so the same concept can be applied on strain. So in order to calculate the new stress or strain at a new direction x prime, we just need to do a coordinate transformation calculation. So you can look at the detail in textbook, but here we just want to show the result. Here is the transformation equation for stress and strain, and you can see the original value of stress theta, sigma x, sigma y, and tau xy, or in strain that's epsilon x, epsilon y, and tau xy, can be used to calculate for the new stress at x prime and sigma prime simply by multiplying a bunch of cosine and sine, and this is a typical coordinate transformation equation by rotating the coordinate. Okay, so we want to look at the strain equation. The transformation strain equation is important because we're going to talk about how to measure these three important. That's in practice how we measure these three variable in experiment. That is sigma, epsilon x, epsilon y, and gamma xy. Okay, so we can take this equation out and look at this in detail. So in order to know these three unknown, we need to have established three equations by plugging different value of theta and measure the strain. Okay, so using this concept, we in practice we have some set of strain gauge. They mounted at a certain structure, certain pattern. So the first structure, we call it strain rosette. The first rosette is 45-degree strain rosette. That is the angle between two strain gauge are 45 degree. There are second type of strain gauge rosette. That's a 60 degree rosette. Okay, these three strain gauge give us three equation by plugging different value of theta. Take this 45-degree strain rosette for example. Strain gauge A give us the theta equal to 0. So if we plug in theta equal to 0, we get epsilon x equal to epsilon A. Epsilon A is the reading on the strain gauge A. Okay, then if we substitute theta equal to 90 degree, that gives us epsilon y equal to epsilon c, and epsilon c is the reading from strain gauge C. Okay, so now we are going to use this, the value of strain gauge B. So if we substitute theta equal to 45, we can get an equation like this. Okay, this helps us to solve the shear strain gamma xy equal to 2 times epsilon b, that's the reading from the strain gauge B, minus epsilon A plus epsilon C. Okay, a different equation is given here for 60-degree strain rosette. Okay, so we can use this method to determine the state of stress. That is the three important value, epsilon x, y, and tau and gamma xy. Okay, once we get this three value figured out, the transformation is just by plugging different value of angle theta. So, but this has some drawback because it's hard for us to visualize how these two value changes with the different value of theta, right? It's pretty hard because the equation is pretty much complicated. The second, it's hard to do optimization. So we don't know at which angle we have the maximum value or minimum value of sigma x. Same for the shear stress. We don't know which angle we have the maximum value of shear stress. The same problem apply on this transformation equation of strain. Okay, so in order to solve that, in order to have better visualization how this strain changes with angle, and to find out the maximum value of normal stress and shear stress, we use a tool called Mohr circle. Okay, so let's talk about how to make a Mohr circle. First, so here let's take an example to how to make a Mohr circle for stress. Okay, first we want to plot a 2 point. Each point have the x value as the normal stress value, and the y-axis value as the shear stress value. So the coordinate system of Mohr stress is different from our traditional coordinate system. That is the XYZ usually indicates the space or location. On the Mohr circle coordinates, we have the x-axis, that is normal stress value, and the y-axis has the shear stress value. Okay, so we just plot the first dot here. And the second dot, we use the normal stress on the orthogonal direction, that is sigma y, with minus shear stress. Okay, then we have 2 points. The next we're going to do is we're going to connect these 2 points by a line. Okay, then on this line, we can know the center of this line is the center of the circle, of the Mohr circle, and the length of the line is the diameter of that circle. Okay, if we use this value, center and diameter, we can draw a circle looks like this. Okay, this Mohr circle is very important because all the possible orientation it described on the circle, and it gave us for a given orientation, it gave us the normal stress and shear stress. Okay, so once you have the Mohr circle, there are three important points, three interesting points. So the first point is here, which gives the maximum normal stress. We call it theta 1, and the second interesting point is sigma 2, sigma 1, sigma 2, and the Mohr circle on sigma 1, sigma 2 has the shear stress of 0. That means on that orientation, it has either the maximum normal stress or minimum normal stress, but with no shear stress. We call that principal stress. We usually use sigma 1 and sigma 2, and sigma 1 larger than sigma 2 to indicate what the first principal stress and second principal stress. Okay. So another interesting point, the third interesting point, is on to the top of this circle. That says tau maximum. So the tau is the height of this point gives the maximum shear stress. Okay. So the height of this value is equal to the radius of the Mohr circle. Okay. Okay. Another interesting thing is we actually can find out the angle, the rotation angle on this Mohr plane. Okay, if we use this phi, so for example, this is the first principal stress, and we found out what's the angle between the x-axis to the first principal stress. So we just need to find out the angle tau, tangle phi, and phi equal to 2 times of theta, and that the theta is the actual rotation angle from the principal stress to the axis x. Okay, so the similar step can be used to make a Mohr circle of strain. Instead, the only difference is here we have a strain of tau, but here we use the strain over 2. That is gamma over 2. The rest are exactly the same. Okay, so let's go through an example. So let's look at this thin wall pressure tank, and on the surface we have a set of 45-degree strain gauge roll set. Okay, A, B, and C that's separated by 45-degree angle. So from the reading, from the reading of strain gauge A, we get the strain value as 201 mu epsilon, and the strain gauge B give us 311 mu epsilon. And strain gauge C give us 189 mu epsilon. What we want to calculate is first, I want to calculate the normal strains epsilon x and epsilon y and gamma xy, and x is the same orientation as the strain gauge A. Then we want to calculate the principal strain epsilon 1 and 2 and the maximum value of the shear strain. Then we want to calculate the angle between the principal strain epsilon 1 and to the strain gauge A. Okay, how are we going to do it? First, we want to calculate the normal strain epsilon x and epsilon y and gamma xy. So we're going to use this strain roll set equation at 45 degree, and we can use this equation. If we substitute epsilon A equal to 201, epsilon B equal to 311, and epsilon C to 189, we get the value looks like this. Okay, epsilon x exactly equal to epsilon A, that is 201, epsilon y equal to 189, and the shear strain gamma xy equal to 272 mu epsilon. Okay, so now let's move on to the second step. We want to calculate the principal strain epsilon 1 and epsilon 2 and the maximum value of the shear strain. To do that, we need to draw a Mohr circle. Okay, so we need to use draw 2 points given the value we calculate here. The first is we use the epsilon x on the x-axis, and half of the shear strain gamma xy here. If 272 divided by 2 give us 136. Okay, that's first point. The second point, we use the epsilon y on the x-axis, that is 189, and the y-axis is minus 136 mu epsilon. Okay, so these 2 points, once this 2 point has been established, we draw a line. So we can determine the center of the Mohr circle. Okay, also we can calculate the radius of the Mohr circle. Okay, the center of Mohr circle is just the average of 201 with the average of 201 and 189 give us 195. Okay, the center is on the horizontal axis. Okay, so we have a shear force of 0. The radius of the circle, we just simply using this equation. The 136 is the shear stress, is the shear strain, is this line, and 201 minus 195 is this small line, and that gives us the radius of 136.1 mu epsilon. Okay, so once we have the circle figured out, it's the next are very simple. The principal strain epsilon 1 is the center plus the radius. Okay, that gives us epsilon 1 equal to 331, and epsilon 2, that is the center minus the radius, that is 195 minus 136, that gives us 58.9. Okay, and the maximum shear strain is 2 times of the radius, and we get 272.2. Okay, so that's step 2. So then we want to calculate the angle between the principal strain and to the strain gauge A. So we need to find out the angle phi. So do some simple calculation. We get the A tangent of 201. That is this line. That is the y coordinate of this dot. And 201 minus 189, that is this small line. So we get 86.5 degree. Since the real rotation angle is only a half of the phi, so we get the rotation angle that's equal to 43.5 degree. So if you look at this angle, and the principal stress is actually very close to the strain gauge B, so that gives us almost the same value. The first principal stress, the first principal strain gave us almost exactly the same value as a strain gauge B here.